I'm going to go in and I'm going to turn off shadows so that I have that extra stuff. So the model population, I kind of fill up the warehouse, which is kind of slow, and I could probably do a better job of making it less full, where you instantiate an item when it's needed. But I just decided, oh, I'm going to create a big, full warehouse, and so it takes a little bit of time to ramp up to populate the model with all the items. And also this is my dev version of FlexSim, so it actually runs slower than the release version of FlexSim. But okay, so you have here, your AutoStore model with stuff stacked up. And I've made it so that you have these blue ones and these green ones. And I have made it so that I think, yeah, so these ones are encouraged. If you are on one of these ones, then you are encouraged to travel this direction. And if you are on one of these ones, then you are encouraged to travel this direction. And I think I give you, the way that I do it is in my AGV network, I have a custom multiplied by custom path cost. And I do some calculations, which is, so I also have AGVs with different orientations. So for example, this AGV right here is kind of pointing, I guess, in this direction, and this AGV is pointing in this direction. And their main yellow box is hovering over kind of where they're loading the item, but then they have this extension of the driver that extends out from where their yellow box is. And for each one of them, I have, let's see, I get a value on this guy, which is, I have this is up AGV label on that guy that essentially tells me what his orientation is, right? So this is, I guess, guys oriented this way are an up AGV, and these other guys oriented the other way are, their is up AGV value is 0. And then for these paths, we have an up AGV affinity value that is 1 or 0. And so when those match, then I just give it the standard path weight. And when they don't match, then I multiply by a wrong orientation path multiplier, right? And that's in my parameters. I say a wrong oriented horizontal path gets a value of 1.6. So I'm multiplying whatever the distance that you might want to travel on that path by 1.6, which is essentially saying I want these guys to travel on these horizontal paths, this one or this one, right? So these are the ones with the up AGV affinity of 1. So this path and this path and this path, right? And then the other ones have an up AGV affinity of 0. So this path, and this path. And when it calculates, when does the routing algorithm, it will say, okay, well, I want to test how long, what is the cost of traveling from here to here. And if the AGV affinity does not match the label of the guy, then I'm going to give it an extra cost. So that essentially says, I'm not disallowing people from traveling on those edges, but I am saying I would like you to travel on these edges, and I would like you to travel on these edges. And what that means is that it decreases the likelihood that they're going to run into each other, because you're not going to cross halfway over each other. Usually you'll either be going this way or this way. And if you go this way, you'll be yeah. So that's the one way. And then we also have this cost multiplier, which is if it's not traveling forward on the path based upon that path's orientation, then I multiply it by some other path reverse cost multiplier. So again, this is a path reverse cost. So if you do both, if you travel backwards on the path in the way that I don't want you to go, and you you're wrong oriented, then you're going to kind of get a double demerit, which is 1.5 times 1.6. And that one is, these guys are oriented, the blue ones are oriented, meaning I want to prefer AGVs that are traveling on this path to travel down in this direction, and AGVs that are traveling on one of these two paths will travel up. I want them to travel up in the up direction. And if you're going in any other direction, then you get a demerit. So that's kind of the soft deadlock avoidance mechanism, which is encourage people to travel in their lanes, right? Any questions on that?
So Anthony, basically you give a lower cost, right? If you follow the preferred path, right?
Yeah,
And
so I give it
the
standard cost if they travel the preferred path, and then I tack on extra cost if they don't travel on the path that I want them to.
Okay, and since each vehicle that occupied 2 grids, like essentially you control that, like for example, for that the vehicle on the right side, so that can only occupy that 2 green line, right, when it's travel.
So you like from the AGV, like internal logic of the AGV, the internal logic of the AGV really only cares about kind of the center of the yellow box and where he is traveling, right? So technically this guy, if I'm gonna slow it down. I don't know if this is answering your question, but I'll explain, and maybe hopefully that will help out. So when he is traveling, so he's traveling along here, right? From the AGV's logic, the AGV system really only thinks that he's traveling from this, or from this point to this point to this point to this point, right? The AGV system is not technically aware that this other guy, this part is hanging off, right? And so the AGV system only cares about traveling, right here. It's only thinking about, I'm traveling from here to here to here to here, right? And so by the fact that he is, and I've put on some extra tacking on logic to say, well, technically the AGV system says, just sees him as traveling from here to here to here. And by the fact that these guys are oriented in that direction, right? And he's going, he's traveling on the correct lane, right? Because his middle lane is this top one, which is this up AGV affinity is 1, and this this is up AGV is 1, so they match, right? And so he's giving it the standard cost, saying you don't get a demerit because you're traveling properly here, right? So if it were to, you know, somehow travel down his the center of his yellow box was to say travel down here and then go over, then it would give him a demerit, because first of all, that would be a single demerit, right? Because he's traveling in the correct direction. He's going on this one, but he's traveling, these two labels do not match, right? So this is up AGV affinity, or up AGV affinity is 0, but this guy is an up AGV, meaning he's oriented this, you know, this certain way. And so that does not match that label. So when it looks at the cost of traveling from here to here, it's going to give it a demerit, saying that that's extra cost because technically you shouldn't be traveling there.
Hey, Anthony, this is Anish. I had a follow-up question on that. So you said the AGV network only knows about the like the left side of the thing which has the tote on it. So how do you ensure that something else is not traveling on the adjacent lane coming like
on this one? You mean
so
traveling
because
over this?
there might be something which is traveling against the preferred path, right?
Yeah.
On the adjacent, and there's a possibility of collision at that point because the AGV won't know that there is
So that's kind of that's jumping a little bit ahead to the what I would say the hard path allocation mechanism. So I've just talked about kind of the soft path avoidance mechanism.
If you're gonna cover it ahead, you can continue and we can skip.
So this is just, you know, this logic right here, and by the fact that I've set these labels properly, essentially, you know, encourages these guys, you know, a guy who is oriented this way, and if he's traveling this way, should travel such that this yellow box is over the top of this lane, right? And if he's traveling the other way, then it's going to prefer him to travel on this one, where his yellow box is over this blue lane, right? So if he were to turn around and travel the other way, he would probably travel this way, then move up 2 spaces and then move down, so that it makes it's soft, but it makes it so that generally people will stay in lanes that don't run into each other, right? Okay. And, you know, for this guy who is oriented the other way, if he's going up in this direction, it's going to encourage him to be on this lane. His yellow carrying point is going to be on this lane. And when he travels down, it's going to be on this lane, right? So that even people who are oriented differently will still travel in the same lanes so that they avoid each other. Okay, so that's the soft one. So now let's talk about the hard one. And so again, as I mentioned, the fact that the yellow box is, you know, it just thinks about the yellow box and where the center of the yellow box is oriented. The default allocation mechanism, and you can see here, these orange lines here, they are what define the allocations, okay? And so the basic rule of the AGV is it kind of plays hopscotch on the control points. So it tries to allocate a control point, and if it cannot allocate a control point, it cannot travel to that control point, okay? And so it'll stop at its current control point, wait until it can allocate. And then once it can allocate, then it can move forward to that control point. The standard AGV mechanism, again, only looks at the control points that he's traveling over, which are this orange line or these two orange lines. So this line right here that goes to that control point that he's on top of, and this other line right here, which is to this control point. So you can see, as far as the state goes, he has currently two control points allocated, the one that he's over the top of, and then the one that he's traveling to. Okay. These other two lines are lines that I have enforced on the object. So I have added these allocations as custom allocations that through code, and I can show you that code. But if I were to not add that code, then you would see that it would just be these two lines that you would see, meaning he only allocates the control points that he travels over. And that's problematic because, one, if you have a guy who's oriented differently, right? If a guy is the other way, then he's just going to allocate these control points, whereas this guy just allocates these control points, and they could run over each other and not know at all that they're running over each other, because they're allocating completely separate control points and think they're fine. So I have added these two control points, and this is the part where it's not finished. I need to tweak that code so that it gets it right, especially on turns. I think I've got it correct when you're going straight down a section, but then if you stop and then turn and go up or go down, then it gets off. But let me show you where that is. Let's see, it's the AutoStore robot process. And it is it's this one, custom allocations. So I have this on build travel path, and I think that's a new trigger that's available for 23.0 that I can listen to, which is as soon as I think this happens. So there's let's see. Maybe I'm getting ahead of myself. I'm going to go to docs.flexsim.com. And I'm going to go to I think it's on this page somewhere. Let's see. Dang it, it's one of these. It's in the customization. Yeah. Okay. I guess it's in reference tools, AGV network. So there is there's a talk about a customization delegate, but also there's in here, it kind of documents a sequence of things that happen whenever you fulfill a travel task. One is you resolve routing. So it uses Dijkstra's and or A star. And then it builds a travel path, which essentially once it's figured out the routing, it builds, it essentially says, I'm going to go from this location on this path to here, then I'm going to switch over to this path. So it creates this sequence of path sections that become the travel path. Once it is finished building that travel path, it fires this on build travel path event. The big thing is when it builds this travel point path, it also builds a list of allocation points. So it says, at this point, I need to allocate this control point. At this point, I need to allocate this control point, and so on throughout the whole path. So it's building this sequence of sections, but it's also adding these these kind of allocation points where it says, here I need to allocate this control point. And I would suggest, when you have time, go ahead and read through this section. I think it has some pretty good information on various logic. Okay, so sorry, back to what I was talking about. So once it's finished building the travel path, then I can listen to it and I can fire my own code. What I can do there is I can add my own custom allocations. And I have not looked at this code in a while, so I'm probably just I'm looking at it with you. Hopefully I can kind of explain kind of what it's doing. So one, the AGV has this allocation points attribute or property that you can access that says, here are all of the points where I need to stop or where I need to allocate a control point. And if I can't allocate that control point, then I need to stop. And so I go through each of those, and it looks like I'm pushing it to an array. And then I go through that array. I'm creating a local array, and then I go through that array, and I kind of look at that control point allocation. And I think I use control point connections. Let's see. It's up. Right. Yeah, so I use control point allocations, which are the hangover connection. Okay, so each one of these control points has, if I actually show in my AGV network, I've hidden them, I think. So if I say control point connections, I have an up connection and a down connection. And if I show them, you'll be able to see that each one of these, this control point essentially has a relationship so that it knows the neighboring control points. So I guess this would be the up control point for this control point, and this would be the down control point. And the reason I use that is based upon the orientation of the AGV. And so what I want to say is, okay, I'm going to go through and look at these allocations. And if I am traveling horizontally, then I know that either I need to add allocations for control points neighboring it in this direction, or for control points neighboring it in this direction, depending on the orientation of that AGV. And so I use this up and down connection so that I can know, oh, this is this control point. I know based upon that, and then I look at the orientation of the guy, and based upon that, I can know, oh, here I need to look at the down connection. And then in that case, I essentially add an allocation point for that control point that has the exact same, an allocation has a stop distance, which is the point at which you would need to stop if you cannot allocate forward, okay? So that's the stop distance. And then you also have a traversal distance, which is the distance at which you can release or you can remove that guy. And then also you have an arrival distance, which is the point at which the center of your object has arrived at that. And so when you can add an allocation point to this AGV based upon that control point, and then I essentially use the same distances as the point that I'm looking at, whose neighbor I'm looking at. This is probably the big one right here, which is if I'm traveling horizontally, then I need to add these additional allocations for that. And if I've done that properly, then what it will do is it will try to allocate, and then whether or not, depending on, no matter which orientation you are going, if if one guy is stopped and has allocated a certain point, then another guy will have to wait because he cannot allocate those points, and he's doing it on both lanes, right? And so that will work properly. And then if you're going in different directions, then it's going to recognize, hey, this is deadlock, and then let you then do some logic to get around the deadlock. Okay. So this is the is left right. I also have to do if I'm going up and down, I have to adjust the stop and traversal distances. So for example, if this object, say this object were traveling up this lane, I'm going to move this out of the way. If this object is traveling up in this lane, it only takes one lane, but by the fact that it has this extra distance trailing off of it, then it needs to increase the traversal distance, meaning I need to go farther before I can deallocate that control point. So I'm adjusting, if I'm traveling upward and I have a trailing edge, right, I'm going to increase the amount of distance that I have to travel before I can allocate a given point. And if I'm going in the opposite direction, where my trailing or my hanging point is in front of me, then I need to decrease the stop distance, which means I need to allocate earlier, right? So that when I stop, I'll stop that much earlier, so there will still be that much amount of space in front of me, so that I don't, stop. If I don't do that, then he'll stop right here trying to allocate this point, and he'll have already overrun that point, right? And so that's kind of this main logic right here, which is, if it's one way, then I need to decrease my stop distance. If it's the other way, then I need to increase my traversal distance. And then, these sections right here are the main pieces of logic, and the other pieces of logic are kind of edge cases. If I'm on my first one, then I have to do some special stuff, etc. And this piece of code is probably the big piece of code that I need to tweak that isn't perfect yet. That I need to figure out, okay, how do I do this right? Especially if I'm traveling horizontally, and now I'm stopping and then traveling this way, how does that affect how I allocate these things, and so on. So, again, I've talked a lot here. Any questions that you guys have?
I have a question, Anthony. So basically, after the path has been built, you have a allocation point list, and in this trigger you modify it. So instead of one lane, you make it like a 2 lane, right? So added the neighbor lane point to that list, right?
Yep.
And
so
my question is, oh, sorry.
Yeah. Go ahead. Yeah.
Yeah. My question is, after you modify the list, but the AGV travel on the land, those are the dynamic. So how you control when when you travel on the land, you properly allocate the point from the other land. Like, what's the logic to control that?
Yeah, so that's this logic right here, which is, so, so I have my list of allocation points, and each one of them is associated with a specific control point that I need to allocate, right? And so if I build, if this guy is, I guess it works. Okay, so if I'm gonna run this real slow so that I can just see him running. Okay, so if I just were to let it go and do its own thing, then it would only allocate these control points on right here. And when this code fires, that's what I see in the AGV's allocation points array. Okay, so I'll see, once it's built its travel path, I'll see, oh, this node, I'll see this node, I'll see this node, this node, this node, right? If he's traveling down this way. Mm-hmm. And what I need to do is I need to say, okay, well, he's traveling horizontally. And I know that when he's traveling horizontally, he's going to take up 2 lanes. And so I need to add more things to his allocation list, right? So I have a set list of these things, but I also need to add to that list these control points right here. And the way that I do it is I get his orientation. I say he's an up AGV. I call him an up AGV in that this direction is the positive Y. And so his main point is pointing up. His carrier is pointing up relative to the other part. Okay. And so I get that is up AGV. And then I know from that I need to get from this control point, right? In that list, I'm going through that list. From this control point, I need to get access to this control point. And the way that I know that is based upon this control point connections, these control point connections that I've added, right? So in my AGV, I have an up and a down, right? I have an up and a down. And so for this guy, if I'm talking, so in my algorithm, say I'm looking at this guy right here, he's going to have an up connection that points to this one, and he's going to have a down connection that points to this one. And by the fact that I know this AGV's orientation, I know that I'm looking at I want to look at the down connection, okay? And so I look at the down connection, and that gives me access to this control point. And then I call this method, which essentially says, I want you to also allocate this control point. And I want you to allocate him at the same time that you need to allocate this control point. And I want you to release him at essentially the same time. I think I offset it by some amount, 0.1 or something. And I'm not sure exact, maybe it was just trying to get it to work, right? But I want you to deallocate him at about the same time as you deallocate this guy. And then I go through that list again, or I go to the next point in the list, which would be this guy. And I do the same thing. I say, okay, well, you're still traveling horizontally. And I know this is an up AGV. So I'm going to look at the down connection, and I'm going to look at this guy. And I want to add an allocation point to your list for that guy for the exact same stop distance and traversal distance as this guy. Hopefully that answers your question.
Yes.
Okay. So, Anthony, one more question.
Yeah.
The on-build travel path, is that getting triggered every time you have an allocation?
No, it's triggered at the beginning of a travel task, which is, when he finishes loading this, this part, then he'll have a destination. You need to go, to this location at the end, or to this drop-off location. And so on build travel path, it'll build the entire path to that location. And then it'll fire this on build travel path, which is saying, I just built the travel path. Is there anything you want to do? Yeah.
Got it. So you could have another drive on that exact same lane where your allocation, you cannot allocate because that control point is already allocated. That's when you'll have deadlocks for this case.
Yeah. So if some other guy decides, hey, I want to go on this lane in the other direction, right? Then he's going to build the same thing, right? He's going to say, oh, or the default maybe says, allocate this control point, this control point, this control point. And then it calls the on build travel path that fires my code. And that code is going to say, I also need to allocate this control point, this control point, this control point. And so when he then travels in that direction, when they try to allocate, it may be this one, and I may be adjusting it, slightly adjusting it so that like one of them is preferred or happens first. I'm not sure, but that may be something that I may want to do, or I do. But the idea would be, yeah, when you hit that, then you would get into deadlock. And that is this on deadlock trigger, which is I match a value. I have the event is actually called on AGV allocation failed, which is when a given AGV tries to allocate forward and he cannot because that control point is taken by somebody. Then it's going to fire this on at AGV allocation failed. And one of the parameters, and this is a new feature in 23.0, is this is deadlock. And I want to match that with the value 1, which means yes, I only want this to fire if it's a failed in allocation and it's deadlock. And so then that will kick this process off. And I think this process is very similar to what was described in the Kiva model, which is, so say I've got this other guy and he's traveling this way and he's trying to allocate this control point, but that one's allocated by this guy, right? So what it's going to do is it's going to essentially say, okay, I'm right here. I'm trying to allocate to this guy. I'm going to pick one in the cycle. I'm going to pick one of these guys, and I'm going to take all of the other guys in the cycle. In this case, it would just be 2, but take whoever they have currently allocated, right? So if I'm this other guy trying to travel this way, and I want to preempt him to move out of the way of this guy, then I'm going to go look at this guy and take all of the control points that he has currently allocated, which is these 4, and I'm going to set their routing constraint to blocked. Okay, and what that will essentially do, and then I will preempt this guy who's going this way from his current task, and then make him start that task again. Right, which is essentially just saying, stop what you're doing and then start it over again, which will re-trigger the routing algorithm to say, how do I get there? But now, by the fact that I'm in this deadlock and I've implemented this routing constraint, it's going to say, when I route, I cannot go here, 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 or here. And so in that, when it tries to do that routing algorithm, it'll say, well, I can't go there. So it will try to route around, and it'll use whatever routing algorithms it uses.
Copy.
Okay. Does that make sense? Any questions there?
I have a question about the running speed, like
Yeah.
so when you run the model, like what's the speed looks like with like multiple AGVs?
Yeah. It's I guess there's an initial startup that's kind of slow populating the model. It's not super fast. And you have to realize this is my dev version of FlexSim. So in real life, it'll be faster as well. It'll be even faster than this. But it isn't, it isn't super fast, specifically because it has to use, it can't cache the paths, specifically because it's using these dynamic routing constraints. It uses A*, which is kind of a guided algorithm to the destination to try to find the route to the destination. But especially when you are in deadlock, it can't really cache those paths. It has to rebuild the path every time. And so it does have a slowdown. It's not as fast as standard AGV models.
I see.
So
But it seems really fast, right?
Yeah.
Like 10 times, right? Even in the debug mode.
yeah, well, I wish it was faster. So
That's
So,
cool.
so you rebuild the path only when you have deadlock, right? Otherwise, you're not considering other drives when you're building the route table, or you're not setting those routing constraints because a bot is there in a specific control point.
yeah,
right?
yeah. So that's, yeah. So right now I'm doing it simple, right? Which is assume, right? Give these soft rules, right? I'm using soft rules to say, try to get in this lane. But when I do the route, I'm not specifically, when I create the route, I'm not kind of looking at current state of where things are. You could do that. You could do that. Like there's, you could, trying to think. In here, you could, you have this multiplied by custom path cost. And this could, right now, this is really just, a lot of this state doesn't really change. Well, I guess, this state does, right? Whether or not the AGV is currently digging. But a lot of this other state doesn't necessarily change during the model. It's just comparing a static label on the path to a static label on the task executor. But that could be some dynamic state thing where maybe when you're on a certain path, you say increment, or when you build the travel path, you could go through your travel path and say increment some traffic label on that path, right? And then once I'm finished with that path, I go back through and decrement that travel path label. And then in this custom path cost, you can then look at what that label is on the path and say, well, if there's a lot of people going on this path, in the next 3 minutes, then maybe I should not go there, right? But that would all be part of this. You could implement that all as part of this kind of custom path cost. I think it will, if you do that, and this is probably something you should remember is you should make sure that it always builds it in A* mode and not in Dijkstra's mode. And the thing that triggers it to be in A* mode is there's at least one routing constraint in the system that is not its standard. And so the way that you could do that is just have a single control point somewhere in your model. It doesn't even need to be locked to a path. And just when you start your model, you set its routing constraint to blocked. And then at that point, everything will use A* mode, which means every single time it builds a path, it will use the dynamic A* route building. So then it will recalculate this every single time. I think there's some in the documentation. I think there's some discussion of, when it builds Dijkstra's and when it builds A-star. The difference between Dijkstra's and A-star is Dijkstra's is it builds the entire table of, it builds it by destination. So for a given destination, it will build the entire routing table saying, if you want to go from here to here, this is how you get there. If you want to go from here to here, this is how you get there. In A-star, it's saying it's not going to cache that table, right? In Dijkstra's, it builds the entire table and then it caches it off so that it can use it later. With A-star, it says, well, I can't cache this off because it's probably going to change every single time. And so it uses a guided algorithm where it tries to kind of go toward the destination as it builds out its decision or its routing. And so it's a little bit, it's faster to build once, but by the fact that you're in A-star mode, you're building it a lot of times. And so overall, it'll be slower to be in A-star mode than in Dijkstra's mode, but it's kind of the, I guess, the requirement of if you're going to have dynamic routing on every single travel operation, then you need to use A-star. So
does Anthony, does the soft coding versus the hard coding that you talked about earlier, is the soft one, will it run faster because it does cache, or are the rules simplified, or
yeah, I think this one is set up so that by default, when it's not doing the deadlock, when it's not routing around deadlock, it's going to cache the paths, which will make it faster. Although, even here, the size of the table is so big, sometimes it's not even worth it then to use, because you have to realize there's like 10,000. If there's 10,000 nodes here, the table, each row in a table is going to be 10,000 wide. And so if you have 10,000 by 10,000, that table is going to use up a lot of memory. And it may be that you don't actually reuse them that much. So it's kind of a, there's pros and cons to using both. So. Any other questions?
One of the things, and probably this is possible, so one of the things we could see is, like, if you have an idle bot, let's say it's not parked, and it's on the way, you would go through the same process of deadlock, and you'll be able to push it out of your way. I've seen in few other softwares there's a possibility of looking up ahead into your allocation path even before you allocate, like you know the route, so probably the control points, and see if there is a bot in your path, and let's say it's idle sitting there. If you want to bump it out of your way, right? So that you don't have to come to a stop or decelerate.
So what you could do, that's possible. What you could do is, let's see. So in here, let's see. Yeah, so in this add custom allocations, so you have these allocation points. So that's the list of control points. When you build your travel path, that's the list of control points that you're going to allocate. So you kind of have, here are all the spots on my path. And then that allocation point, it is an instance of if it's agv.allocatable object. So this is my control point equals, I just say agv.allocation points. And I'll just say the first one, give me the first one. And that control point, you can get its current allocations, So it's a list of objects who have allocated it. Usually that's only going to be one because you set your max allocations on it to be one, or it'll be 1 or 0. So you can look at the current allocations. You can look at requests. So if there's anybody requesting an allocation on that, but in your case, what you probably do is just look at the allocations. And that each one of these is a AGV. I think that's an allocation. Oops. Yeah, an allocation point. So you could say point equals allocations of 1, and then you can say point, and you can get all of the information on that allocation point. So you can get the AGV that has allocated. There's a an arrival distance, which is that AGV, his distance at which he arrives at that node. You have a stop distance. You have an object, which would be pointing to the control point itself. So it's kind of a two-way pointer, and other stuff. So quest state, which is the state. If he's allocated, then it would be allocated state. But the main one you'd probably want to get is the AGV. So then you can say, okay, here's all the points that I need to allocate on my path. Are they currently allocated? And you could, give that guy a task to say, hey, move out of the way if he's idle, right? Or you could say, maybe you could have your guy travel on a path that's different and by preempting him and saying, oh, well, there's a guy here, or maybe if it's a hot guy or somebody who's stuck there that that you won't be able to move him out of the way, then you could say, well, preempt me and put routing constraints at that point where he is, so that then I route around him altogether.
Got it.
Yeah. So yeah, this implementation is somewhat lazy, meaning I just take the shortest route and then deal with allocation issues. But you could be more proactive. So
yeah, this is super helpful. Thank you.
Anthony, could you is this all if let's say that there was in the sequence in all the AGVs that are part of this, let's say there were 10 that were like high priority AGVs, can they lock down an entire path, or would that be inefficient? Maybe that would be really inefficient.
Yeah, I mean, these are good questions that simulation is intended to to explore, right? Which is, if I'm a high priority guy, do I put certain information on the path that I'm going to as I'm going to it, so that other people avoid me? All of those things are like good questions.
No,
like, how does this affect the overall throughput of the system? So